In fact, no, I don't have one like this in the example set. If you had a channel that just hypothetically, let's say it's a QAM system, here's f sub c minus 1 over 2t, f sub c plus 1 over 2t, and my channel looked like this. Okay, I got no energy down here, so this is not good. Okay, what would happen is that the phi of f that you had tried to use to make this look flat, essentially, is going to have some kind of infinite. And unfortunately, when you go to normalize that, or when you try to invert this, you're going to pull, if you make this a normalized basis function, then when you invert it, the gain is going to go down. The signal-to-noise ratio is going to go down in the channel. Or if you don't make it normalized, you essentially increase the transmit power. So not quite. Your intuition's in the right direction, but you gotta deal with the transmit power increase in that case. Okay, so two cases where the types of things that we'll be talking about are used. Voice band modems, always one of my favorite examples. I guess I was raised on these things a long time ago. Everybody's got one, but they tend to be almost commoditized these days. But that voice band channel, that telephone channel that's used for one of these dial-up modems, okay, is not a nice flat channel. Kind of looks like this. And so that's your H of F. And what happens, of course, is they want these modems to go as fast as they can, so they try to stitch a QAM signal in there. And it may go from frequencies as low as a few hundred kilohertz, a few hundred hertz, so let's say 0.3 kilohertz, up to maybe a little bit above 3 kilohertz. So most of these modems will actually adapt the actual symbol rate and carrier frequency so they can try to fit the QAM signal into the channel like that. Or some of the modems will actually try to do PAM and live with that same characteristic, but they'll have PAM running in there. Now, obviously, that channel is not flat. Okay, it's going to be pretty severely distorted. You've got a nice fast symbol rate, though. The wider this transmit spectrum, the faster the symbol rate. So that means more messages being transmitted. So what are we going to do about this? Well, we're going to try to flatten the channel in the receiver. So you asked about doing it in the transmitter. We're going to try to do it in the receiver. The equivalent of the energy blowing up to infinity in the transmit side is going to turn out to be the noise being blown up in the receive side. It's called noise enhancement. We're going to learn how to try to best compromise between increasing the noise power and improving the transmission rate for such a system. So the basic idea that's suggested here is essentially we have a filter, 1 over H of F, filters that signal I was calling YP of T at the output of the channel earlier. And the hope is that if I have 1 over H of F, of course, times H of F times phi of F, then I'm going to get phi of F, and if I designed a good basis function to begin with, I'm going to preserve that at the output of the channel. So that's in fact what voice band modems do, is they try to equalize the channel. And an equalizer is simply a filter that kind of looks like 1 over H of F. And so one of the topics we're going to see is equalizer design. Digital TV doesn't usually kind of conjure up this image of a channel that's not flat. You say, well, analog TV transmits there. It's wireless spectrum. Why would we actually get any kind of non-flatness in the channel? Well, if I were to look at channel 2, for instance, in transmission here, at least in the United States, it's 6 megahertz wide. It goes from 50 megahertz to 56 megahertz. The carrier frequency is not in the middle. 52 megahertz. If you go back and look at single sideband and vestigial sideband, which are equivalent to QAM, you'll see in section 2.4 you can put the carrier frequency anywhere, and they actually do that in digital TV. It doesn't really matter. You could have put it at 53 also in the middle. It wouldn't have made any difference, but it is what it is. But we would normally think wireless channel, okay, what's causing any kind of filtering? Well, the issue is that the path between that TV antenna, wherever it may happen to be, somewhere up on top of a mountain, and your TV somewhere else, okay, is that, yeah, great, if there's a straight path here, you will have essentially a flat channel. But if that signal bounces anywhere else, off the ground, off a mountain, off some metallic object, then there are two paths. And the delays on the two paths may be different. So you'll get a version of the signal plus another version of the signal, maybe of the same order of magnitude, but delayed. And at certain frequencies of transmission, that delay will correspond to being 180 degrees, which will mean that the delayed path has a negative of the signal that you're receiving. So it'll actually cancel itself. And this is called multipath distortion. So what's going to happen when you do this is you're going to see the channel looking like that. And this frequency of repeat as you roll through the various frequencies, F, whether you're at 180 degrees or you're at 0 degrees, in which case the signals will reinforce when you're at 0 degrees, depends on the frequency. And the greater the delay, the more compressed this rippling will occur in the channel. So this causes intersymbol interference also. So that's a terrestrial transmission. Anyone want to try to think about this in your cable system? What might cause this? You get cable TV, you figure, no problem. I'm covered. We don't have bouncing off mountains inside the cable itself. Yes, sir. Yeah, that's exactly it. And in fact, if you have an upstairs TV and you pull off the TV, it's even worse because you have an open circuit at the end of your coax. We all know what happens when a signal goes down an open circuit. It hits the open circuit, it gets reflected 180 degrees out of phase. It'll come back, and depending on the delay of that connection in the coax again, it could actually cause us to have this same rippling. And in fact, if you've got a cable network inside your house and you've put a bunch of extensions on this illegally, and you're noticing certain channels are getting knocked out when this happens, that's exactly what's happening. Those signals are bouncing. You need to go in and actually put something in that blocks the return signal from getting back from these things. This can also happen with your neighbor's house on the cable system, and they try to engineer those systems so that the return signals are blocked. Okay? Now guess what happened when they tried to do bidirectional cable modems? Okay? Then they were really screwed. They had to go back out to all those places and things and replace them with filters that didn't block the low frequencies. Remember we talked about cable modems being below 50 megahertz, the lowest TV channel in the upstream direction. Well, that all got blocked in the original design. So they had to spend billions of dollars to go out and make those blocking parts only 50 megahertz and above. There's a question back here.
Sir, no matter how many multipath you have, you'll have a sinusoid in the channel? Or?
Well, it would depend. That's for two paths. If I had three paths, I'd have to add them all together, but there would be certain frequencies where I could get constructive or destructive interference. So it depends on the number of paths that are bouncing and exactly what the delays and amplitudes are as to what the channel would look like. But it's very unlikely to look like it's flat unless there's just one single path that's making it through. So cable TV has this also, and as you might guess, your portable phones have this in spades. There are times when we want to throw them at the ground because they're just about as worthless as being broken on the ground because they keep dropping the call while you're talking to somebody. Is kind of annoying, and it is in fact again this same type of effect where you have the rolling kind of channel position depending on, now just replace this by a cell phone here instead of a TV, and you get this rolling characteristic. And if you have relatively narrow QAM slacks, okay, you could actually lose the whole signal in this case, which is really bad for transmission. So you'll see some of the better cell phone techniques that have less dropping of calls. The GSM was one step in this direction, which is originally the European network, but came into the United States. It uses QAM signals that are 270 kilohertz wide, rather than the original digital telephone system were only 30 kilohertz wide, and then they actually multiplex many users onto the same carrier frequency, and then your cell phone picks off your particular version. The wider you get, the more chances you have to have some good energy getting through the channel. Now, you're going to have to deal with the non-flatness in one way or another, but you deal with that. So the wideband CDMA actually uses signals that are a little over a megahertz wide in terms of transmission. There are many users multiplexed into that single transmission band. Okay, so reasonable delays can cause this rippling in characteristic, and that means we get intersymbol interference in the channel, and so we need to do something about it. And what we're going to do is put something in the receiver that tries to mitigate this non-flatness, tries to return the signal to be flat, and that's called an equalizer. And to get to equalizers, to try to make an assessment of what are good approaches to equalizer, what are bad approaches to equalization, I'm going to introduce some basics for characterizing a receiver. We're going to look at some bounds and say, okay, how well might we be able to do? It may not be optimum, but what can we expect to see? And how much then would it cost us to design a system that does about as well as one of these equalizers might be expected to do? So in this world of suboptimality, symbol by symbol detectors and equalizers, the first thing that we're going to postulate we could do in a receiver is to run through a basis function which is matched to the pulse response itself, and we're going to normalize the pulse response, so we can always normalize a function by dividing by its norm. So integrate the squared energy in a function, you get some number for that, and then divide by the square root of that, and that's the norm for the system. So this would be P star minus T over norm P, which we could compute if we know the pulse response, we know the channel. We would be able to do that. And then we would sample at all the right times. And instead of writing capital T minus T and realizing I'm sending successive messages, I realize that the actual filter is 5P minus T. That T or 2T or 3T that I was adding is just a phase difference. Okay. You take the Fourier transform, you just see there's an e to the minus j term that's dependent on what you offset the time argument of the filter. So we get that corresponding time offset just by sampling at all the symbol periods. And we proceed to call that y of k, and this will be y of t right here. So the reason I put a p earlier was because I knew I was going to presume I'm running through some kind of match filter. We know match filters are good. They maximize signal-to-noise ratio in some sense. So I have that maximized signal-to-noise ratio signal here run through a sampling device, call that y sub k, and at this point I break ranks with everything I've seen earlier. At this point we really haven't lost anything in terms of optimality. We know that we can go through a set of match filters. If I think of this 5p of t here in this sampling device as simply a set of match filters in time, I could always do a linear transformation on that to some orthogonal basis function. I could do Gram-Schmidt on the whole set over time, get a set of basis functions, and I would simply have a linear combination of one set of basis functions being these functions here. So I haven't really lost anything going through the channel at this point. And then I'm going to say, well, at this point, I'm going to do some kind of processing. It's probably linear, since the basis sets are equivalent anyway, could be absorbed here. I'm going to call that a receiver. And the output of this receiver at time k is zk, and that is going to be sent to the symbol-by-symbol detector. May not be optimum, but I don't want to wait forever for my decisions. I can't group things into packets and look at large super symbols with lots of sizes there, but I may do some level of processing to try to help myself out. And there may be some delay inherent in the actual physical implementation of any processing that I do here. That's fine. I'm sampling at every instant. It just means that my symbol-by-symbol detector correspondingly is deciding messages maybe 10 symbol periods later in time, or maybe 20 symbol periods later in time, depending on the delay through the channel, through this match filter, and through any receive processing that I'm doing. So that basically I'm deciding at the right time the messages, they have to be inside the receiver to be able to do that. So in this section here, nothing's lost. But by the time I get over to the end of the system, that's no longer true. And what I would like to do, whether this is suboptimum or not, is to model the entire channel, which starts over here somewhere and finishes here just before the symbol-by-symbol detector, as xk in discrete time, the message at time k, being corrupted by some additive distortion, which I call the error sequence, E sub k. That'll include any noise that gets processed by the system, and it will include any intersymbol interference that my receiver has not been able to eliminate at its output. So E sub k is both noise and residual intersymbol interference. And all that system together produces this output Z sub k, which then is going to go into a symbol-by-symbol detector. And I'm going to pretend that this additive distortion is essentially the old additive Gaussian noise channel again. In fact, even if the error signal is not white, I'm going to treat it like it's white because I'm doing symbol-by-symbol detection at that point. And what I really care about is the variance of the noise at time k, the variance of the error, I should say, at time k, and the signal power that made it through to Z sub k. And so I will have then a signal-to-noise ratio, which I'll call the signal-to-noise ratio for any given receiver R, which is going to be Ex bar, the energy of the symbol part that made it through, divided by sigma E squared. And if this is complex system, then if I find the variance as a complex number, I'll need to divide by 2 to make this energy per dimension on top and bottom. So I could write signal variance divided by the number of dimensions over distortion or error variance divided by dimension. And at that point, I say, well, hopefully since a lot of things are still getting added together here in this distortion, that's probably still close to Gaussian, and so I know I can approximate, may not be an upper bound anymore, my probability of error by the number of nearest neighbors times Q times some, let's call it kappa, times a signal-to-noise ratio. Kappa for things like PAM is 3 over m minus 1. For square QAM, it's 3 over m squared minus 1. For the 32 cross, we got another formula we can stick in there for kappa. But basically, better signal-to-noise ratio means lower probability of error. So I'm going to characterize my receiver by a signal-to-noise ratio. And the justification I provide to you is I say, well, even if my distortion is not quite Gaussian, all right, so what? I'm going to postulate that higher signal-to-noise ratio means lower probability of error in a system. And I'm going to target signal-to-noise ratio as the thing that I want to improve or to optimize. And that is going to be independent of the actual signal constellation. If I know whether it's QAM or PAM, complex or real, different number of points in the constellation, so what? if I've maximized the signal-to-noise ratio for any of those types of constellations, I will have the lowest probability of error in my receiver. So one of the things I'm going to try to do here with R is to set up its structure within certain limits of complexity so that I maximize the signal-to-noise ratio. If I do that, I'm going to say I've done a good job. Yes, sir.
So when we have complex signals, shall we count that as 2 dimensions or 1
Yes.
dimensions?
There are 2 real dimensions, and whenever I normalize to the number of dimensions, I mean real dimensions. In
Okay.
any 79 course here at Stanford, I consistently use that definition. So better SNR, lower PE. Whether or not the SNR is dominated by residual intersymbol interference or noise or some even